I am looking at the air between my hands. It looks like nothing. I used to think that if I took everything away, every atom and every bit of light, I would be left with a total blank. I thought emptiness just meant absence. But I was wrong about what happens when you have nothing left. Here is the thing. We have this deep-seated intuition that empty means nothing is happening. If you clear the furniture out of a room, you say the room is empty. If you suck all the air out of a jar, you say the jar is empty. We tend to think of space as a blank stage where things happen. But the stage itself is not supposed to do anything. But in physics, nothing does not stay quiet. It can be pushed on metal plates. It can shift the energy inside an atom. It can even produce light if you shake it hard enough. This creates a massive problem for our common sense. If nothing is there, how can it have a physical effect? We must stop thinking about the vacuum as a hole or a gap and start thinking about it as a physical state. It is the quietest possible state the universe can have, but it is still a state. I want you to picture a room that never becomes perfectly silent. You can take out the people, the clocks, and the hum of the fridge. You can seal the windows to block the street noise until there is nothing left for your ears to catch. But even then, the room still has a shape, and it still has air that can vibrate at certain notes. It has a background hiss that you can never quite turn off, because the room itself is a physical thing that supports specific patterns. You might call it quiet, but that silence is the property of the room, not just a lack of noise. It is a state of the room, where the vibrations are at their absolute minimum. If you could look closely enough at the air, you would see it still has structure, even when no one is talking. This is the first step to understanding the vacuum. The quietest possible thing still has a pattern to it. Now, think about what happens if you move the walls of that room. If you make the room very narrow, some of those deep, low notes cannot fit anymore because their waves are too big for the space. The silence in a narrow hallway sounds different than the silence in a cathedral because the environment limits the patterns the air can form. You have not added any sound, but by changing the boundaries, you have changed what silence is allowed to do. This is exactly how I have come to think about empty space. It is not just a void. It is a system with constraints. When you put two objects close together, you are essentially changing the shape of the vacuum between them. You are restricting the patterns that the fields can take in that small gap. Just like the room, nothing in a tight space is physically different from the nothing in the open air because of those boundaries. So, what is going on? In modern physics, I do not think of space as just a big, empty box. I think of it as being filled with fields. There is an electron field, an electromagnetic field, all sorts of them, layered everywhere. When we say a place is empty, we just mean those fields are in their lowest possible energy state. We call this the vacuum. But here is the trick. Lowest energy is not the same thing as zero. In quantum field theory, the vacuum is a physical state with its own structure. Rather than a true blank nothingness, even when there are no particles around, the fields are still there, existing in their ground state. It is the quietest they can possibly be, but that quiet still carries a physical reality. You see, every one of those fields I mentioned is made up of different patterns, or modes, that behave like tiny quantum oscillators. Think of them like little weights on springs. In the old, classical way of thinking, You could imagine a spring coming to a total, frozen stop at the very bottom, where it has zero energy. But quantum mechanics gives us a different rule. Because of the math behind how tiny things move, every single one of these oscillators must have a minimum amount of energy. We call this zero-point energy. Even if you could cool a region of space down to the absolute lowest temperature possible, you would still be left with this tiny bit of motion. This is the part that gets me. You can never take that last bit of energy away. Nature simply will not let the field stay perfectly still. So even though the vacuum is the lowest energy state, it still has this unavoidable quantum structure, a jitter that is baked into the universe itself. This is why the vacuum is not a blank hole. It is a field that cannot stop vibrating even when it is supposedly at rest. But here is the problem with how we talk about this. I have heard people explain this by saying the vacuum borrows energy from the future to make particles pop in and out for a split second. It is a catchy story, and it helps people visualize something happening, but it is not the cleanest physics. Nature does not really run on a credit card system where it gets to break its own laws if it pays the energy back quickly. The truth is much deeper. That energy is not being borrowed at all. It is already there. It is the inherent, unavoidable background energy of the universe that can never be flattened to a true zero. When you look at nothing, you are seeing a field that simply has a floor higher than we expected. We do not need to invent a loophole for the law of conservation of energy, because that energy is a permanent, physical part of the ground state itself. And that leads to another story we tell about those virtual particles you hear people talk about. You should not think of them as real little marbles flying around or popping in and out like tiny bubbles in a soup. In physics, they are what we call off-shell objects. That is just a technical way of saying they do not follow the normal rules of real particles. They do not have a fixed mass. And they cannot exist on their own as free particles. They are not little beads living in space. They are more like a mathematical way for us to calculate how the field's ground state reacts to its surroundings. They are the fingerprints of the vacuum's structure, not a literal crowd of matter appearing from nowhere. This is where it gets interesting, because we can measure it. In 1948, a physicist named Casimir realized that if the vacuum really has structure, it should leave a measurable footprint. He came up with a simple setup. Imagine two uncharged metal plates placed incredibly close together in a region of space that is completely empty. Now, remember that analogy about the silent room and how moving the walls changes which notes can fit? That is exactly what happens here. Between those two plates, the space is so tight that only the shortest field patterns can squeeze in. But on the outside of the plates, the space is infinite. So every possible pattern, big or small, can exist and press against the metal. Because there is more variety in the patterns pushing from the outside than from the inside, real physical pressure is created. It is like having a large crowd of people outside a building, pushing against the walls, while only a few people are inside, pushing back. The result is that the plates are shoved together by the nothing surrounding them. It is not gravity, it is not magnetism, and it is not a breeze. It is the Casimir effect. For decades, it was just a strange idea on a chalkboard, but eventually someone finally tested it and found the force was exactly where it was supposed to be. Think about that. Two neutral objects with absolutely nothing between them are being pushed together by the physical reality of emptiness. It is the hidden structure of the vacuum finally becoming visible. But I must be careful here. When you hear about the Casimir effect, it is tempting to think we have finally found a way to weigh the entire energy of the vacuum, or that we have discovered a magic battery for the future. It is not quite that simple. While the force is real and measurable, it is mostly showing us how the quantum fields interact with those specific metal plates. It is a beautiful confirmation that the vacuum has structure, but it is not a trivial one-sentence proof for every wild idea about zero-point energy. It is a subtle shift in the balance of the world's quietest state. We have found a fingerprint, but we have not caught the whole ghost yet. There are other fingerprints too. If you look at an atom, the vacuum nudges the electrons and shifts their energy levels ever so slightly. This is called the Lamb shift. And it was one of the first major clues that the vacuum was not just a blank background. It is like a tiny, invisible breeze is constantly rattling the parts of the atom, and we can see the result in the light the atom gives off. But the most dramatic thing happens when you start moving the boundaries themselves. If you take a mirror and shake it, incredibly fast, near the speed of light, you can kick those vacuum fluctuations and turn them into real, glowing photons. This is the dynamic Casimir effect. You are essentially turning silence into a shout. You take a region where there are no particles. You move a boundary back and forth, and suddenly, light appears out of the dark. Those photons did not come from the mirror. They were shaken out of the field that was already there, just waiting for enough energy to be kicked into reality. It is a stunning demonstration that the vacuum is a physical, responsive thing that does much more than just sit there. There is a reason for all of this, and it goes back to a fundamental limit. In 1927, a physicist named Werner Heisenberg was trying to understand the rules of the microscopic world. He wanted to answer a simple question. Can we ever perfectly define exactly where a particle is and exactly how fast it is moving at the same time? He was looking for a way to reach a state of absolute precision. But what he found was a wall. He discovered that there is an inherent fuzziness and uncertainty built into the very fabric of nature. You can never get the world to be perfectly sharp or perfectly quiet. If you try to pin down a field to a state of absolute zero, it starts to jiggle. Heisenberg found that exact classical quietness is not the right picture for our universe. There is a hard limit to how still things can be. And that limit is the reason nothing is not nothing. Think about that. Heisenberg did not hand us the whole modern vacuum story in 1927, but he helped kill the last hope that the microscopic world could ever be a perfectly silent stage. He opened a door. And as quantum field theory grew, we realized that the impossibility of stillness was not just about particles. It was a property of space itself. This result changed how I think about what nothing really is. It means the vacuum is not a blank stage waiting for physics to happen on it. The vacuum is already part of the physics. We spent centuries thinking of emptiness as an absence, but now we see it as the quietest possible state of a very active universe. The silence was physical all along. But here is the biggest mystery of all. When we move from the tiny gap between metal plates to the scale of the entire universe, the vacuum starts to look like a much bigger player. There is something we call dark energy that is making the universe expand faster. And a leading possibility is that this is simply the energy of the vacuum itself. If space has this inherent ground state energy, it will essentially push outward on everything. So, back to that silent room I described at the start. It never actually became perfectly silent, because I have realized that the silence itself is a physical part of the room. You can take everything out of the universe, every atom, every photon, but the fields themselves are still there, and they still have that fundamental, unavoidable hiss that you can never turn off. You have just learned that silence itself has patterns, and the walls you build around it change the song it is allowed to play. Emptiness is not an absence. It is a state. And as we have seen, that state can press. It can shift, and it can even